Welcome to this series of lectures on data structures. In today's lecture, I'm going to walk you through the code that I had implemented to convert an infix expression to a postfix expression using stack. So this is one of the many applications that a stack abstract data type has in computer science. We studied about the applications in the previous lectures, and in this lecture we're going to talk about the infix expression to postfix expression conversion and look at the code. There are some key concepts that I would like to review before we go on and look at the code. The first one is the input expression, which is the infix expression, is scanned by our program from left to right. So there is a tokenizer that scans the expression from left to right. For instance, if you have an expression of the form a plus b, this is scanned from left to right, and the tokens are generated one by one. And the tokens can be an operator, which is the plus, which also includes the opening brace and the closing brace, or the tokens can be operands, which are nothing but the variables. And in this particular demonstration, I'm going to use digits, so it's easy for me to demonstrate the postfix evaluation later on. So there is a precedence associated with each and every operator. The relative precedences of operators are listed here. So you have the opening brace, which has the highest precedence, and then you have the exponentiation, which has the next highest precedence. Star and division, multiplication, division have the next highest precedence, and so on. The operators are also associated with what is known as an associativity property, which determine which side of the operator is evaluated first when you encounter more than one operator of the same type in an expression. So when we say that exponentiation is right associative, it means that the right occurrence of exponentiation is evaluated before any of the left occurrences of the exponentiation. For instance, if you have an expression like a exponentiation b exponentiation c, b exponentiation c is evaluated before the a exponentiation b. Similarly, you have associativity property attached to the operators multiplication, division, addition, and subtraction. These operators are left associative, and exponentiation is right associative. One point to note is that we have a stack that we maintain, which contains operators as we parse the expression from left to right. One rule is that whenever we have an operator that is being checked whether it can be pushed onto the stack or not, the operator is pushed only when its precedence is higher than the precedence of the operator that exists on top of the stack. Otherwise, the operator which exists on the top of the stack is popped out and given to the output before this operator is pushed in. So as long as there are operators in the stack which have higher precedence than the one that's coming in, all of those operators are pushed to the output before the operator that is coming in is pushed into the stack. Operators never go to the output without having to spend some time on the stack. If the precedence of the operator that comes in is higher than the precedence of the operator that is there on the top of the stack, that operator gets to be pushed onto the stack. And that is because the operator that comes in has to be applied on the operands before the operator that's already present in the stack, because this has lower precedence than this operator. One behavior of the closing parenthesis is that it pops out all the operators from the stack until the next open parenthesis is also popped out. So if you have the stack and you have an open parenthesis and you have bunch of operators that exist on the stack, as soon as the closing parenthesis comes in, you pop out all of these operators till the opening parenthesis is also popped out. And we don't have any operand stack for infix to postfix conversion. Operand stack is only used for the postfix evaluation, which we'll talk about later. So here is the precedence function that we have written. So this function gives the precedence of an operator outside the stack, and this function gives the precedence of an operator inside the stack. As we know, open parenthesis has the highest precedence of all the operators, and then we have the exponentiation, which has the next highest precedence, and then we have the operators of multiplication, modulo, and division having the next higher precedence, and then we have the plus minus having the least precedence. So this is the right precedence of operator, because we are talking about the precedence of the operator outside the stack, and because we are scanning the expression from left to right, the operator that is outside the stack is right side to the operator that's already inside the stack, because that would already have been parsed, which means that that operator was to the left of the current operator. And this operator precedence is the left precedence of the operator. So as we had seen, the opening parenthesis will have the least precedence once it's inside the stack, and the relative precedences of other operators don't change. Exponentiation has the highest precedence, and then we get the multiplication, division, and modulo operators, and then the addition and subtraction operators. One thing to note is that depending on the associativity of the operators, we have different precedences for the operators in the out precedence and the in precedence. For instance, if you take plus minus, the in precedence is 2, but then the out precedence is 1, which means the in precedence is higher than the out precedence, which means that the left precedence is higher than the right precedence. And this is fine because the operators are left associative. So if you have an expression of a plus b plus c, you need to make sure that a plus b is evaluated first, and then the rest of the expression is evaluated. In contrast, if you take a look at the out and in precedences of exponentiation operator, the out precedence of the exponentiation operator is higher than the in precedence. That's because exponentiation is right associative. And if you have an expression of the form a exponentiation b exponentiation c, the right side is evaluated first, and then the left side is evaluated. So coming to the meat of the function, which is this convert infix to postfix, it accepts two inputs. First is the expression that is to be converted, which is the infix expression. And then the right part is the output, which will be the converted postfix expression. We create a operator stack with this statement, and we scan the input array from left to right. So we initialize I to 0, which is the leftmost index, and we check if the ith character is a digit. As I said, I'm using digits as operands instead of symbols like a, b. So if it's a digit, I straight away pipe that character to the output. If the input character is not a digit, if it's an operator, I check whether the stack is empty. Because if the stack is empty, I don't have any precedence checks to be done between the operator that's coming in and operators that are already present in the stack. So I just push the operator onto the stack. But if there is something in the stack, I check the precedence of the input operator that's coming in. If that is less than the precedence of the operator that's on the top of the stack, then I can't put that operator onto the stack. So I have an operator here, and there is an incoming operator, and if the precedence of this incoming operator is less than the precedence of this operator present in the stack, I can't put this on top, because the precedence of this guy is higher, this operator is higher, it has to be evaluated before. So I pop it out, and I do that till I encounter some operator in the stack that is at the top which has lesser precedence than the operator that's coming in. So this logic is a core logic that ensures that the precedence and the associativity of the operators is honored in your postfix expression. So this popping out happens as long as my input operator has lesser precedence than the operator that is there on the stack. And once this condition is broken, either because the stack has become empty or because I encountered some operator on the stack that has less precedence than the operator that has come in, I break out and then push my input operator onto the stack. Otherwise, the special kind of logic is applied for the case where you have the input operator as the closing parenthesis. As I said, when the closing parenthesis arrives, all I have to do is to empty out the stack until the next open parenthesis. So all the operators are popped out and then added to the output expression. So this is what this part of the code takes care of the closing parenthesis. And once you are running out of your input characters, you forcibly empty your stack. So this logic takes care of emptying your stack. Please ignore this print statement for debugging, but you just pop out the character out of the next character out of the stack and then output that in your, assign that to your output array. So that's it. This is the code logic that is used for conversion of infix expression to postfix expression. It has 3 steps. Operands are directly put onto the output. The incoming operators are checked for precedence with respect to the operators that are already on the stack, and the right parenthesis logic, which empties out the stack till the next left parenthesis which exists in the stack, and left parenthesis also is popped out of the stack. And the 4th bit of logic is to empty out the stack after you are done with consumption of the input.